In the name of Allah, the most gracious, the most merciful, all praise is due to Allah, and peace and blessings be upon the messenger of Allah, our master Muhammad, and upon his family and all his companions. Now as for what follows, by time indeed mankind is in loss, except for those who have believed and done righteous deeds, and advised one another to truth, and advised one another to patience. This is the inspiration for a national revival. The summary of operating the directional protection relay can be condensed into 3 points. It must all be met together as an end gate. The first point is that the fault current value must be higher than the pickup current value. As for the second point, the value must exceed a certain threshold. The third condition that must be met is that this fault should be within the operating zone. To test the value, we need to meet 2 conditions, and we adjust the current until we verify its value. So we achieve 2 conditions. Adjust voltage, angle, and current. Ensure current is above threshold and angle is correct. 3. To test the value, we ensure that the current value is higher than a certain threshold and that the angle of the current is within the operating zone. We adjust the value until we confirm this value. As for testing the angles, we meet 2 conditions and adjust until we are sure of their values, ensuring that they are functioning correctly. Faults can cause operational issues or incorrect functioning of the directional protection. A 3-phase fault increases current and decreases voltage, complicating the use of voltage as a reference signal for fault current direction. Is it forward or reverse? A face-to-face fault changes voltage angles, affecting zones and potentially misidentifying fault directions. High impedance faults may produce currents below the directional protection setting. The directional protection needs 3 conditions to be met as an end gate. This fault causes a rise in current and a drop in voltage. How can I rely on low voltage to determine fault current direction? Is it forward or reverse? A face-to-face fault changes some voltage angles, affecting zones, leading the relay to misinterpret fault direction. A high impedance fault generates low current below the directional protection setting. Directional protection needs current, voltage, and angle conditions met. If fault current is below the setting, it won't operate. New ideas are sought to avoid these issues, focusing on a fixed reference using voltage to determine fault current direction, whether forward or reverse. Voltage shifts can mislead the relay. High impedance faults may prevent operation. To address these issues, a fixed reference using voltage to determine fault direction has been explored. Modern numerical releases use symmetrical component analysis, determining fault direction through positive, negative, and zero impedance angles. If the fault current is below the set value, directional protection won't operate. Alternative ideas focus on a fixed reference using voltage to determine fault direction, forward or reverse. This is the classic concept for directional protection. Modern numerical releases use symmetrical component to determine fault direction by analyzing angles of positive, negative, and zero impedance, with positive sequence impedance as 3V13I1. The classic concept for directional protection. Conversely, modern numerical releases rely on a new principle using symmetrical component to determine fault direction. The direction is determined from the angles of positive, negative, and zero impedance. Together they equal V1 over I1, and negative sequence impedance is Z2, which is V2 over I2, and Z0 equals V0 over I0. Positive sequence impedance is denoted by the symbol 67, positive or 67B. And when we take the 3 together, it equals V1 over I1, while the negative sequence impedance equals Z2, which is V2 over I2, and Z0 equals V0 over I0. In directional protection, using positive sequence impedance is denoted the symbol 67 positive or 67B. Or negative sec impedance is 67 negative or 67Q. Zero sec impedance is 67 0 or 67G, 67 cube. Positive sequence is always in fault, before and after. It appears alone in balance or 3-phase symmetrical faults, negative. Understanding the symmetrical component reveals that the positive sequence is always present in all faults. It appears alone in balanced faults. The negative sequence appears in unbalanced systems or faults. The zero sequence appears if the ground is involved in the fault. In symmetrical faults, no zero sequence is present. Thus, in a symmetrical fault, only the positive sequence appears. The negative sequence component appears in the case of an unbalanced system or an unbalanced fault, while the zero sequence component appears if the ground is part of the fault. By fault here, we mean an unsymmetrical fault. If I have a symmetrical fault, like a 3-phase to ground fault, there will be no zero sequence present. Therefore, From what has been mentioned, we can say that if I have a symmetrical fault, only the positive sequence will appear. If I have a phase-to-phase voltage, it will show me the positive sequence and the negative sequence. However, if I have a phase-to-ground voltage, it will show me the positive sequence, the negative sequence, and the zero sequence. And we have the positive sequence and the zero sequence. The purpose of using symmetrical components to determine the fault current direction is that its value increases significantly after a fault occurs, making it clear. Using normal voltage can confuse the relay. The area for the is as shown in this diagram is what we call the and the direction of is the sequence resistance, while the y-axis is what we call the positive sequence reactance. The forward direction will be towards the positive sequence impedance of the line, which is called Z1 line. Here we use the maximum torque angle as before, so the maximum torque angle rotates counterclockwise with respect to the R-axis as the reference. The sequence resistance is on the Y-axis, known as the positive sequence reactance. The forward direction points to the positive sequence impedance, Z1 line. We use the maximum torque angle, rotating counterclockwise from the R-axis to measure the push sequence impedance angle. If this angle is between plus 90 and minus 90 degrees relative to the maximum torque angle, it is in the forward zone. If it passes 180 degrees, it is in the reverse zone. The negative and zero sequence impedances also direct towards the positive sequence impedance, Z1 line. Measure the push sequence impedance angle. If it's between plus 90 and 90 degrees, it's in the forward zone. If it passes 180 degrees, it's in the reverse zone. For negative and zero sequence impedance, the forward and reverse zones are opposite to the positive sequence impedance. Some manufacturers multiply negative and zero sequence impedance by 1 to align the forward zone boundaries for all. Of impedance, zero impedance. The boundaries of the forward and reverse zones are opposite to those in the positive sequence impedance. Some manufacturers multiply the negative and zero sequence impedance by -1 to align the forward zone boundaries for all sequence impedances, avoiding engineer confusion. Adjustments were made due to difficulty in accepting the reverse zone. When testing the positive sequence impedance angle, change the voltage angle, not the current angle. Adjust the voltage angle while keeping the current angle at 0 to get the correct angles. Z1 equals V1 at angle A over I1 at angle B, so Z1 will be at angle A minus B. Because some engineers struggle to accept forward and reverse zones reversed relative to positive and negative sequence impedance, the adjustment was made. Now, when testing the positive sequence impedance angle, prefer changing voltage angle over current angle. Goal is to get correct angles by changing voltage angle. Z1 V1 at angle A, I1 at angle B, so Z1 angle A, B. Many directional protection topics like mobilization, close-into-volt cases, and superimposed components are not covered here. For more, refer to scientific papers, research, and relay manuals. So we set B0 and change angle A. As we mentioned before, the boundaries of the forward zone are plus or minus 90 degrees relative to the maximum torque angle passing through 0. There are many topics and ideas related to directional protection that cannot be covered here, such as mobilization, close-into-volt cases, and superimposed components. For more information on these, you can refer to the scientific papers and research related to relay protection, as well as relay manuals.
The remarkable renaissance of a nation